Okay, before I do another, and I may not do an entire circuit one more time, but I want to kind of give a little wrap up and kind of summarize some of this. If you recall, back in the 1950s when transistors were first built, they would actually have to take an entire, multiple transistors to build this AND. They're called AND gates. They had to take more transistors to build this gate, more to build this, more to build the NOT, connecting these with wires. So all these were hand built with transistors. And hopefully now you'll better appreciate the integrated chip that came in the 1960s, because what they did was they basically made the transistors so small and packaged all of this into one. Let me see if I can zoom out one more time so you can see the whole circuit at once. And they basically package this so that all the circuits, all the transistors, and let's draw a, and so kind of erase, let's see if I can erase this top part up here. Oops. Let me erase this real quick so I can use this space here. Oops. And then, those bus X, Y, and Z would come out of the chip. So imagine this was a chip. I could then put voltage into this wire, no voltage in this wire, voltage in this wire, and then have an answer come out here and here showing my actual answer. And I didn't have to build all this. All this was built into a little chip that you just dropped into your computer. And now in the 1970s, when they introduced the microprocessor, the CPU, this is just an adding, right, circuit. And it only adds very small numbers. Well, they may have 32 of these adding chips in a row in order to add a 32-bit number, each of them doing 1 bit. So all 32 of those were in one chip you could drop in. In addition to that, all the 32 that were subtraction and multiplication and literally hundreds of other mathematical operations were all built together into one chip. So hopefully now that you see the circuit, you can kind of better appreciate what is inside of the CPU and the integrated chips and so on. Now, I want to cover one important concept that will kind of show you how this actually works. And I think for this one, I'm going to create a new document and zoom in again. We have learned two different circuits. Guess I keep going the wrong direction. Sorry about that. Okay, we have learned two different circuits. Now, we've learned a couple. We did multiplication, we did subtraction, and we learned two different adding circuits. So for now, I'm going to focus on the adding circuits. We learned a circuit to add two 1-bit numbers. Kind of messy. And then we learned a circuit that did three 1-bit numbers. And if you recall, this one had X and Y, this one had X, Y, and Z. This one had a C and an S, this one had a C and S, because technically it doesn't require any more bits. Now, these circuits actually have names in the world of computer science. They're very important circuits. They're very famous circuits. This one is called a half adder. So you can put that in your notes. Half adder, because it basically only adds two numbers, which is not very helpful to be adding two zeros. But this one is called you can maybe guess it, a full adder. Now, this circuit here is great to learn, great to be introduced to the concept, but a half adder is not used in computers. Like I said, it was really mainly just to demonstrate how a very small adding circuit worked. But a full adder is used in computers. Now, you may ask yourself, why is a 2-bit, or I'm sorry, a 2 1-bit adder not helpful? I'm going to draw a big. I like changing the colors here. I think that's helpful to make a point here. Okay, not helpful, not used Very helpful, very important. Well, let's look at a problem that you can do with this. The largest problem you can do with two 1-bit numbers is 1 plus 1, correct? So we're going to draw that better, which is 2. The largest number you can do here is 1 plus 1 plus 1, which is 3. It's not that much bigger. Just 2 versus 3 doesn't seem to be that important. Well, here's how it is important. If you recall back a few videos ago when we were adding binary numbers. So a very typical math problem a computer may need to do is, let's say, that plus that. So do you remember us adding binary numbers? So that is a very typical problem. Or even much larger problems like 82,640 plus 92 million. Any kind of number, it can have a lot of ones and zeros. Now let's review this, and let's do this problem one more time. 1 plus 1 is 0, carry the 1. 1 plus 1 plus 1 is 1, carry the 1. 1 plus 0 plus 1 is 0, carry the 1. 1 plus 1 plus 0 is 0, carry the 1. Now normally I would go back and check my work and make sure, but this time I want you to notice something. How many numbers in each column did we ever have to add up? If you notice that the first one, we just added these two numbers, okay? But from this column over, we added a carry and the original two numbers. So there were 3 numbers, as I missed my line here, there were 3 numbers that we had to add up. Then with the carry, there was another 3 numbers to carry, to add up, and then another 3 on this one. Does that make sense? Hopefully you can see where I'm going with this. This problem here, this problem right here is exactly what the full adder does. It adds 3 1-bit numbers. If we could only add 2 numbers, then when it came time to have the carry, let's roll this one more time. We could do that with a half adder. That would be possible with a half adder, 2 1-bit numbers. But when we carried, our circuit no longer handles 3 inputs. It only had an X and a Y. So it can no longer do that. But with a full adder, you can carry. So let me explain kind of how this works. In the last video, I kind of drew a little square. And this time, we'll just call this FA. So all that circuitry, the reason I left it open, all of this circuitry is inside of this chip right here. And let's pretend that these 3 wires are my X, Y, and Z. And my output, I'll draw my output down this time. I think last time I drew it to the side, but this time I'll draw it this way. And this will be my C and my S. Okay, make sense? Let me erase some area here so I can have room to work. Now, as you could probably guess, adding a little number like 1 plus 1 plus 0 is not very helpful. But this is actually a relevant problem, this math problem right here. So this could be a full adder, and they just add another full adder, and another full adder, and another full adder. So let's draw that. Let's drop in, if this was back in the 1960s, they'd have to have an actual extra chip here, and they would draw another one here, and we'll draw a 4th one here. Remember, inside each one of these is all that circuit that you just made. Each one of these has an X, Y, and Z, X, Y, and Z, X, Y, and Z, and they all have outputs, C and S. Hopefully all this is kind of tying together and making sense. Now, when we said 1 plus 1 plus 1 was 1, we wrote the answer, and where do you put the next value? You put the next value at the top of the next column. So, in theory, all we need to do is take this wire here electronically. Remember, it's just a wire carrying voltage. and connect it to the input of this one. So now we have our next two numbers being added of our problem with the carry from the previous problem. And then that carry gets routed into that chip, and this gets routed into that chip. Now, that's still a very small problem. That only adds up to the number 15. Continue doing this, 64 of these in a row, and you can add billions of numbers just by taking the same little chip and repeating it over and over. So now when we want to add a number, these numbers here would go here, 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 and here. You'll never need the Z in the first one, right? Because there's no carry in that. And then these numbers to be added up would go into here, 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 and here, into the Y. Then the answer would come out here. The C, we don't really care about the C that's seeing it. We just want to send the C into the next problem. And then that comes out with an answer. And then that comes out with an answer. And finally, we do need to see, if this has a carry, we enter the 1, both answers. So here we have, this would be our answer. We're going to draw a little box that would hold different 1s and 0s. Does that kind of make sense? And this process is repeated for multiplication, division, subtraction, all math problems. They basically build a very small version of the circuit and then just chain them together in order to add values of millions and multiply billions and find the square root and find the exponents, and all kind of math problems are done exactly in this same manner. So to summarize your notes, the full adder is a 3-bit adder, and the reason it's so important is it is what's used to chain these circuits together to add any size number that you want. All you have to do is keep dropping in more circuits, but your circuitry, if you remember the circuitry, how complex it was in here, it's not going to get any more complex. That is all you need, and all you do is drop in multiple copies of them to add large numbers. Now there's one last topic to cover here, and then we will be completely done. And it is actually a topic that is very relevant to using a computer and especially buying a computer. Okay, so let's look at this one more time, and I'm going to change my pen color one more time because we're going to switch topics here. Let's go with, how about a purplish color here. Okay, there's actually a flaw in this system here. Let's see if you can spot it. If we put 4 numbers into these problems, we have a combination of 0, 1, 1, 0. I'm not doing the same problem. Just let's say numbers are going in here. This adder can immediately spit out an answer. Let's say the answer was 1. But let me ask you a question. Can this adder give its answer at exactly the same time as this adder? We'll give you a couple seconds to think about that. The answer is no. And hopefully you can figure out this adder cannot add until it gets its carry here from the answer to this one, which means this one is waiting for this guy, and this one is waiting on this one, and this one is waiting on this one. So in reality, the answer comes out here, then here, then here, then here, then there, and that there is some time from this point to this point. Now, it is very fast, but it is a difference in time. Now, these values are always 1s and 0s. So let me ask you a question. Let's say you told the computer to do 2 math problems in a row. Let's say it's Excel, and you told it to add up 2 different numbers. It just calculated this number, but as soon as this one came out, it's already adding the next number, and this may have changed to 0 because it's doing the next math problem. So at any one point in time, if you read this number, you may get nonsense. You may get half of 2 different math problems. Okay, does that kind of make sense? So we can't just look at this at one time. I mean, let me back up. Let me say this a little bit differently. Let's say this still has 0, 1, 1 from a previous problem, And now this problem, this computer, this adder is figuring out its answer, and it just spits out a 1. Well, at that exact second, this one's getting ready to do its addition. If I were to read this number, it would be a nonsense, irrelevant number that's just a combination of the current math problem and whatever the circuits were previously. Remember, there are no blanks here. There's always a 1 or a 0 in these bits, and they can be left over from a previous problem. Does that kind of make sense? So the answer to this problem and how they came up with this is they had a clock. They built a clock into the circuits that said only check on this interval of time. So and I'm going to kind of really exaggerate how fast computers are, but let's say it took 1 second for all of these adders for this one to finish, for it to spit out its answer to this one, to this one, to this one, for it to get all these numbers, it took 1 second. So the computer would say, check now, check now, check now, check now. And in between, it didn't check. Like, I don't want to know what numbers are there because you may have bad numbers in here. But I know that in 1 second, I have gotten my good answer. And this is a good number. That's a good answer. Anything in here is bad. There's my next good number. Everything in here is bad. Here's my next good number. Okay? Now, a second I exaggerated because they're much faster than that. Back many years ago in the mid-80s, a computer clock could check all these values at about 1/12 millionth of a second. It's pretty fast. 1/12 millionth of a second. Or, to say that a different way, it could do 12 million problems a second. Does that kind of see how it's the same thing? You could either do one math problem in 1/12 millionth of a second, or you could do 12 million problems in 1 second. Then they got faster. They got to 50 million, and then 100 million, and then 500 million times per second. Well, this clock is named after the German mathematician who worked on this on not computers, but on the idea, this is a physics term, of how many times something happens per second. Generally, we kind of measure these in like a waveform. How many waveforms per second do we see? And one event per second is 1 hertz. You may have heard that term, 1 hertz. So you could say that this computer back in the 80s was 12 megahertz or 12 million hertz. And I told you as the computers got faster and faster, they went to 100 megahertz. And then I remember when they passed 1 billion clocks per second. Well, that means that it could calculate all these numbers. And this is just 5. In modern computers, there's 64 of these chained together, 64-bit computers. It could do 64-bit numbers I remember when it went to 1 billion times per second. And they call that 1 gigahertz. I'm running out of room here. Hopefully you're recognizing these numbers because these are the numbers that you look at when you buy a computer. When you buy a computer and it says it runs at 2.4 gigahertz, and that would be a pretty nice speed there today. They go a little bit faster. You may see 4.0 gigahertz. It's always in GHz. That simply means, and it goes all the way back to these clocks and these transistors, that all 64 of those numbers can come out in less than 1/4 billionth of a second, which would be 4 gigahertz. Megahertz would be million, gigahertz would be billion. So that tells you how fast these transistors can update and chain together and cause the same answer to come out. So if you're ever looking at buying a computer, buying a laptop, it'll mention. Remember we talked about Intel earlier. I know I'm writing all over the screen now, but an Intel CPU running at 3.9 gigahertz, and that simply means that it can process one full group of, whether it's adding or subtracting or multiplying in that amount of time, or that many times they can do an entire per second. So in this case, 3.9 billion math problems per second is basically what that means. I'm simplifying that a little bit because in actual engineering, it's a little more complicated than that. It's a lot more complicated than that, but in simple terms, that's about 3.9 billion instructions per second. So I may do one more video just to recap the entire process to show you exactly what I want you to know. I'll skip all the explanation and the extra kind of discussion and just do one simple problem from start to finish. But this wraps up basically as far as knowledge. Terms you need to know. I do want you to know the term clock and hertz. Clock is how do computers stay synchronized? How do the computer math problems stay synchronized? They use a clock, and the clock they use is how many hertz, how many math problems per second can it calculate. So know the term clock, know the term bus, which bus are these series of lines. You also see that term in modern day computers, a 64-bit bus. That means actually they use 64, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. They use 64 bits, 64 wires at a time to do each math problem, to do very large math problems. So know that. Know what each symbol represents and or not. Know how to connect them. But again, from there, I'm going to demonstrate one more video that shows from start to finish the entire process.